All right, so today we start Chapter 7, and Chapter 7 is all about the systems of linear equations. Up to this point, we've been talking about linear equations, different forms of linear equations, how to, find points that fall on these lines and how that works with the equations, connecting situations with equations. And in Chapter 7, what we're going to explore is our problems that require more than one equation to solve. Okay, and it's not really super difficult, but there's a different level of question that we can solve if we understand that, you know what, there's two sort of situations within one problem, and we're going to try and combine those linear equations. So that's what a system is. A system means really it's more than one. Okay, and more than one what? More than one linear equation. So that's what a system of linear equations means. All right, so in this question here, this is the type of question that we are going to be able to use a system of linear equations, but we're not going to get there just yet. I just want to explain the question, and I'm just going to get you to think about what are some of the possible answers. Okay, so a school district has buses that carry 12 passengers and buses that carry 24 passengers, right? So we have small buses and large buses. The total passenger capacity is 780, so there's 780 kids. Now, if that's where the problem ended, this would be a type of problem that we would have done last chapter, right? So we've got 12 kids per small bus and 24 kids per large bus equals a total of 780 kids, right? And you could find how many small buses and large buses would fit that. So that should be familiar so far, okay? And if you didn't pick that out right away, that's no problem. But the second part here, there's a bit of a qualifier. So it's like, well, we might have a number of different solutions for the first part, but the second part is going to narrow that down a bit. Because the second part of this question says there are also 20 more small buses than large buses, okay? So you have to have that factored in as well. All right. So let's take a look at this question, and without turning the page and looking at this full drawn-out answer, let's just think logically here. 780 kids. Okay, so we've got how many buses would we need? How many 12-passenger buses and 24-passenger buses could we combine to get 780 kids? So why don't you take a half a minute right now and just come up with how many 12-passenger buses, how many 24-passenger buses. Just take 30 seconds and see if you can come up with a solution to this first part, okay? All right, so if you are stuck on this, you can start adding multiples here, and this is not quite 780 if we add these up, right? But you might get to a pair of numbers of each of these buses. So has anyone got to an answer yet, or a combination of buses that would add up to 780 passengers? Any answers yet? Okay, you can keep working. You can do trial and error. You can do 12 times. You can just pick any number if you want. Let's say 15, and try 24 times 13. You can do that, but you might want to keep in mind this second part, right? Which would narrow things down a bit for you. So, for example, if you know that this wouldn't be an option. So what about 12 times, 5, and what about 24? Oops. 24 times, what's 20? I guess the small buses have to be 20 more. So let's say 25 and 5. Okay? So to fast track things here now, if you take into consideration the second part, you can do your trial and error here by making sure that the number of small buses is 20 more than the number of large buses. So what does this work out to? Does this give us an answer that we like here? How close are we? Let's see. 12 times 25 is 300. Okay? And what's 24 times 5? Well, on your calculator, 24 times 5 is 120. Okay? So that's 420. Are we close? No. We need 780. So, has anyone come up with a pair of numbers here yet that would fit this? Okay, all right. So, let's just put that down here. So, 12 times, you said 21, and 24 times how many of those buses? 22. Okay, so you're saying this would work. Okay, that is great. That equals 780. Now, for the first part of this problem, that would be one of the solutions, right? Okay, that's great. Now, this chapter, we have to take into consideration the qualifier. So are there a difference of 20 buses here? No, there's only a difference of one bus. You see that? So now we have to consider this. So I go back to this example. Here I had 25 small buses and 5 large ones. That satisfies this part. So that's very good. This is great, but this is not going to work for this question, is it? So do we have another pair over there? Yeah? Okay, so you said 35 small ones, and then, I keep writing, and then 15? Okay, so let's check this out. All right, so 12 times 35 is 420 plus 24 times 15 is 360, and that adds up to 780. Here we have the right number, and the difference between the buses is 20. Okay, I like it. Now, does everyone see that this is the solution to this problem? There are 35 small buses and 15 large buses. Does everyone see how that is the solution to this problem? Now, you came up with another option, right here, 21 and 22, for getting all those kids transported, but it didn't satisfy the second part. So this is where system of linear equations is going to come in. Guess what? We could write an equation, as I mentioned, for the first part, and we could also write a linear equation for the second part. And we're going to learn how to combine those two and find out where our one solution is. So, an easier way to do this, instead of trial and error, all this calculation, is we're going to set up a system of linear equations, and that's going to be 2 linear equations. So, this is a different way to do the solution. Let's integrate now the linear equations. So, we've got 12 times, and I'm going to make S equal to the small buses. Okay? S is small buses. Plus 24, and let's say L, that's for large buses. Okay? Large buses. And that's got to equal 780 students. And we know that there's different combinations that would work for that one. But the second part of the question says, and this is actually kind of tricky to write, a lot of kids mess this up, so you got to pay close attention. If we are going to write an equation relating small buses and large buses for the second part, okay, you got to be careful. There are 20 more small buses than larger buses. So if we're writing an equation and S has to be related to L, how do I factor in the 20 more buses into this equation to make it true? Because I'll tell you, what happens is students go, and let me just clean this up here. Students do this. They say, oh, 20 more small buses, so 20 plus S equals L. But there's more small buses. So guess what? If we're going to make these equal, you have to add 20 to this side. You see? There's more small buses, so you got to take the number of large buses plus 20 to make your equation. You see that? Okay, let me say that again. This one, okay, the small buses, there's more small buses. Okay, so let's say this is all the collection of small buses. There aren't as many large buses. If we had them all stacked up here, you see, there's not as many large buses. That's what the problem says. And as a matter of fact, there's 20 more small buses than large ones. So in order to make the S and the L in an equation, to make them equal, I have to add 20 to the side that has fewer buses. So the number of small buses equals the number of large buses plus 20, because there are 20 more small buses. Think about it this way. Totally different situation, okay? How many boys do we have in here? Not very many, right? Let's see. 1, 2, 3, 4, 5. 5. How many girls do we have in here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? So there are 10 more girls than boys. Right? So if I were to write an equation, I would have to write the number of boys, that's B, plus 15 equals the number of girls. Does that make sense? Right? So in this case, the girls over here had the larger number already. So I take the boys plus 15. There was 5 and 20, wasn't there? Oh, did I do 5 and 15? Oh, I'm sorry. 5 and 15, so 10 more. I was thinking 20. There's 5 and 15, so there are 10 more. Yeah, my apologies. 10 more. So the number of boys plus 10 equals the number of girls. That make sense? Yes, you could. Yes, you could. You will find, as you do more of these, because I've done millions of these almost, not millions, but close, that if you have an equation with subtraction in it, it's going to cause a bit more problems, because subtracting is a little bit trickier, because with the different signs and stuff, there's more opportunity to make mistakes if you subtract. But you totally could. You could write this equation. Let me get rid of all this now. As, because there's more small buses, you could go the number of small buses minus 20 equals the number of large buses. You totally could do that. That would be totally fine. I tend to go with adding to one side instead of subtracting. Okay? So you could do either, but yes. Okay. You're right. The 780 does not go into this equation at all, because it has nothing to do with students. This first one had everything to do with the number of students that we were carrying. This second one has to do with the number of buses. Right? Yes, that's why you need the two equations, because the answer, okay, for S and L has to satisfy both equations. Okay? So that's an important point that I'm going to write next. The solution must, oh boy, sorry, I can't write today. The solution must satisfy both equations. And that's exactly what we did before we wrote down these actual equations, right? If we went back to this part of our solution, right, we found a solution to one of the situations, but it didn't satisfy the other part of it, right? So this one satisfies both equations. It has, we have 15, okay, that's the large buses, plus 20 equals S, the small buses. All right, and I'm just going to go back to this one that I started with, L plus 20, okay? L plus 20. So you see the large buses plus 20 equals the small buses? So, we're going to basically simplify things, because we won't be able to do trial and error for a lot of these problems. They're going to get pretty tough. So we need to be able to write two situations. Now, if I have a point that satisfies two equations, what does that graph look like? And this one will focus more on next class. But what do the graphs look like if we have one point that's on two lines, two straight lines? It would look something like this. That point is on that line, and that point is also on another line. So the graph would look something like this, where the solution to the problem would also be, what do you call this point? What is this point called? The two lines, what do they intersect. That's right. Okay? So the solution to a system of linear equations on the graph, when you graph the two lines, is the intersection point. So that's what we're going to lead into. I think this next, solving graphically is the next section. So today we're focused on generating equations like this. Today is just about creating equations, so let's just get some practice with that. Let's do one or two together. Okay. Let's just see. All right, example 1 in your text. Example 1 in your text, and it looks like this. Okay. Example 1, right here. So let's walk through this example, just so you can get a little bit of practice seeing something. So this is what it says: create a linear system. So that's a system of linear equations to model this situation. So there's always going to be two parts: one part for one line, one part for another one. The perimeter of a Nunavut flag is 16 feet. And the second part is the length is 2 feet longer than its width. So one of the important things that you need to do when we're doing systems of linear equations is figure out what the variables should be and what they represent. And when you're doing that, you have to ask yourself, what is this question actually asking for? Well, it's asking for, we're trying to find length and width, okay, for the flag. We're trying to find length and width. So L for length, W for width is where probably we want to go, right? So this first part, and I'll just cut this for you. All right, so the perimeter of a Nunavut flag is 16 feet. So guess what that is? That is going to be the width plus the length plus another width plus another length is 16. So what would that equation look like? Well, you could just do this. And if we simplified that, that would be 2W plus 2L equals 16. So there's the first equation that describes this part right here. Does everyone see that? The perimeter. Remember, perimeter is distance around. If we're talking about a flag, it's a rectangle. So you can set your variables equal to whatever. It doesn't matter, x, y. It's best, though, to choose a letter that it will remind you about what it's about, right? Like W, width, L, length, okay? So you should do that. Now the second part is this one. Its length is 2 feet longer than its width. So the length and the width are related somehow. The length is 2 feet longer. So which one is the shorter one? The width. And it's shorter by 2 feet. So let's go W plus 2 is going to equal L. And again, if you want to do L minus 2 equals W, that works too. I always tend towards the addition. Yeah, question? Yeah, if the length was, that's a good question. If the length was double the width, okay, so we had something like this, and you'd have width here, and this was the length, and the length was double the width, then you would go length is 2 times the width. This is different because it's the width plus 2 feet, so it's not necessarily half. Yeah, but that's good. If it was double, that's right, that's what it would look like. Okay? All right, any other questions? All right, so what does B say then? Denise has determined that the Nunavut flag is 5 feet long and 3 feet wide. Use the linear system from part A to verify that Denise is correct. So if we are verifying that this is correct, this means that if we plug these numbers in, okay, insert these into both equations should be true. All right, so 5 feet long. So that means that we should have, let's see, 2 times the width plus 2 times the length equals 16. So the length is 5 feet. How do I know it's the length? Because it's longer, right? So put the 5 there. The 3 is the width here. Oh, it says long 2 and wide. So 3 goes here. Now, is this true? Let's see. That's 6 plus 10 equals 16. Yes, so 3 and 5 fits for that equation. Let's check to see if it fits for the other one. So, length equals width plus 2. Well, length is 5, width is 3. Does 5 equal 3 plus 2? Yes. So we have verified that that these dimensions are correct by plugging them into both equations, and the equations then are true mathematical statements. Okay. If we plug the numbers in and they didn't equal, the left side and the right side weren't equal to each other, then it would not be the right answer. Make sense? Yes? Make sense? Any questions? Okay, so here's example 2 from your textbook, and it says this. Create a linear system to model this situation. In Calgary, a school raised $195 by collecting 3,000 items for recycling. Okay, so 3,000 items for recycling. That's the number of items. Okay, 3,000 items. The school received 5 cents for each pop can and 20 cents for each large plastic bottle. Okay, so there's 2 separate parts there. How can we create 2 equations to represent this situation? All right. So we have now this one's a bit tricky because it's this necessarily not like equation 1, equation 2. Okay, this is all mixed up a little bit, but there's 2 different pieces of information. So one equation is going to be about something, like you mentioned that first example. The first equation was about the number of people. The second one was about the number of buses. So when you have a system of 2 equations, one equation is going to be about one certain kind of quantity. Another one's going to be about something else. So there are, let's do the variables first, that's important. Pop cans and bottles. Okay? So we've got pop cans and bottles. How many pop cans and bottles do we have in total? We have 3,000 items that are pop cans or bottles. So this is your first equation, or one of them. So usually in these problems, you're going to have an equation that's just about the number of things. It's simply going to be one variable plus another variable equals a number. That's going to be usually going to be one of the equations. Now the next one, this one that gets a bit tricky, but the next one is about the money. Okay? So we have 5 cents for each P, pop can, 20 cents for each B, plastic bottle. So do you see there's the second equation in there about money. So one is just about the number of items. The second one now has to do with money. So what you do here is, again, if you want to do cents or dollars, I guess it doesn't really matter, but we'll do cents. So 5 cents for each what? Pop can. So that's 5 cents times the number of pop cans. Remember, P is the number of pop cans. That's what we said. And B is the number of plastic bottles. So 5 cents for every pop can. And we also get, so the plus, so we're adding up all the money, 20 cents for each what? Bottle. All of that money is going to add up to what? $195. Okay, so here's another little twist in this. This is cents and this is dollars. You have to make sure that your units are the same on both sides of the equation. So are we going to write the cents as dollars, or are we going to write the dollars as cents? Cents as dollars? Okay, I agree. I agree. So let's make this $195 in total, and let's change these numbers, $0.05 and $0.20. 0.2. Yeah. Okay, can you change it after you finish the equation? What you can't do, okay, this is what you can't do. You can't say 5p plus 20b equals 195. You cannot do that because you're dealing with cents here and dollars here in the same equation, so that's going to be a totally different line. So no, in a sense, you can't just write it like whatever the question gives you and then change it later. You can't actually do that because this is not the same line. You have to have them both as dollars, like everything in this equation as the same unit, either dollars or cents. But if we used cents, okay, and did 19500 cents, then when you get to the end, actually it doesn't matter which unit you use for this one because you're going to get the same P and the same B anyways. So you can change the units at the end if you want, but when you're doing the equations, they all have to be the same. So just for the record, you can't do that. That's not going to get your answer. Good question, though. Oops. Any other questions? Okay. So again, right now we're not solving this. We're just creating the equations and verifying. So let's just do letter B, and then I'll set you off on your assignment. You can get some work on your own. So the school collected 2,700 pop cans and 300 plastic bottles. Use the linear system to verify these numbers. So those numbers have to satisfy both equations for that to be verified. And so I'm going to do this. 2,700 plus 300 equals 3,000. Is that true? Yes, that is absolutely true. So that satisfies equation number 1. Now I'm going to do this. 2,700 times 0.05 plus 300 times 0.2. That should equal 195. You see how I plug those values into the second equation? All right. So if you do that calculation here, 2,700 times 0.5, that's 5 cents for each one, you get 135 bucks. And then you add that to 300 times 20 cents, and that total is 195. And so this is verified as well. Okay. So this would be your work for A right here, these equations, and this would be the work that you'd have to show at least for B. So I'll just do 5A for you again. Which system has the solution x equals -1, y equals -2? You're simply putting -1 in for x and 2 in for y to see if the equation is true. Okay, so it looks like this. So right away with this first one, it looks like -1 and 2 is not a solution for this first equation. So I guess it's not a solution for this one. If you go to B now, check that one. 3 times -1 minus 2 equals -1. So this is -3 minus 2. Does that equal -1? No. Doesn't look like that's a solution either, so it doesn't fit on this line. So go to C. -3 times -1 plus 5 times 2. Does that equal 13? That's 3 plus 10. Oh, that equals 13, so that's good. Let's check the other one. Yes, it works for that one too. So C, that's a solution for the system in C, but not in